पहले उसको कंप्लीट करते हैं, इसके बाद मॉड्यूल 5 पे जाते हैं। तो मुझे जहाँ तक याद पड़ता है, लास्ट टाइम we discussed various types of dam systems, which are critically dammed system, over dammed system, and under dammed system. And as we discussed that critically dammed system and over dammed systems are of no use from civil engineering point of view, and the only type of system which are of interest to civil engineers are under dammed systems. That is the dammed system in which the damping ratio is less than 1. So in the next slide, I am providing approximate damping ratio for various materials. If we have various structures, but the stresses are low, not more than half of the yield point or ultimate strength, then damping ratio for welded steel, pre-stressed concrete or reinforced concrete design which has light cracking, the damping ratio is 2 to 3%. And reinforced concrete structures with considerable cracking have relatively more damping ratio, 3 to 5%. And in case of bolted or riveted steel and timber structure, the damping ratio is 5 to 7%. However, if the stresses are high, if the stresses are in the vicinity of yield point or ultimate strength, then the damping ratio for same material are increased, because with the increase in stress, the damages or extent of cracking increases. Consequently, the damping ratio will increase. So as I discussed, that from civil engineering point of view, we are interested only in under dammed system. Therefore, in the coming slides, we will discuss a response of under dammed system when subjected to free vibration. Just like undamped system, we can solve to the second order differential equation for underdamped system is of this type, in which A and B are constants which can be determined by initial conditions. And omega D, which is known as damped natural frequency, is undamped natural frequency into 1 minus zeta square under root. And as I said, A and B can be determined by initial conditions, that is displacement and velocity at the start of free vibration at t is equal to 0. And if we determine these values and substitute in this equation, the final equation is is given below. From this equation we can find the displacement response of underdamped system when subjected to free vibration. And just like undamped system, we are interested in peak dynamic displacement, because once we calculate peak dynamic displacement, we multiply it with the stiffness and we get the value of peak equivalent static force. So the dynamic displacement for underdamped systems, the peak value of dynamic displacement for underdamped system can be calculated from this equation. Once we calculate U0, we multiply it with K to get the peak value of equivalent static force. So now we are in a position to solve a problem, and we will resolve the problem 4.2 for damping ratio of 5%. If you remember, in problem 4.2 we were having a frame so we will resolve this problem. In problem 4.2 we consider this as an undamped system. Now we will consider a damping ratio of 5%. So as we calculated natural circular frequency in problem 4.2, which was 34.79 radian per second. From this we can calculate damped natural frequency, which is almost same. Omega n is 34.79, omega d is 34.77. The insignificant change is due to the reason that damping ratio is small. If zeta is 0.05, zeta square will be 0.025 and 1 minus zeta square will be 0.997. Under root of 0.997 is almost equal to 1. So that is why there is no significant change in the values of these two frequencies. From this we can calculate the value of viscous damping coefficient. Damping ratio is viscous damping coefficient divided by 2m omega n, or C is equal to zeta into 2m omega n. Mass is given, omega n is calculated. Zeta is 0.05, so we can calculate C. And we can substitute this value in the equation of motion for undamped system subjected to free vibration. This is equation of motion for damped single degree of freedom subjected to free vibration. And few slides back we calculated, we derived an expression for finding the response of underdamped systems. Using that solution, we can find the displacement response of the system with this equation of motion. And this u of 0, which was given in problem 4.2, was 0.002 feet. U dot of 0 was 0.3 feet per second. omega n, omega d are just calculated. Omega n was calculated, omega d is just calculated. There is small correction. This is 0.003 feet per second. So substituting these values in the Bow equation, we get this equation, which after simplification is in this form. Now, with the help of this equation for various values of time t, we can find the corresponding value of dynamic displacement. And if we draw the plot, draw a graph for this equation, this is the graph that is plotted by using the previous equation, this one. Now you can see, due to damping in every cycle, the peak dynamic displacement is decreasing. In case of undamped system, there is no energy dissipation. Therefore, peak dynamic displacement remains same. Here, now due to damping, you can see the decrease in peak dynamic displacement in every cycle. Anyhow, now we can find the peak dynamic displacement. We have all the values. Peak dynamic displacement comes out to be 0.006 feet, and the corresponding equivalent static force is K into U naught is 24.8 K. So I will wait for a few seconds. If there is no question, I will proceed. Now the reduction in peak dynamic displacement due to damping is known as decay of response. And decay of response due to damping help us in calculating the damping ratio. If there is an existing structure and if it is required to find the damping ratio, we conduct free vibration test on the structure. We provide instruments in the structure before testing, and during free vibration we record the displacement time response of the structure, and once we record that response and plot that recorded data, we can calculate damping ratio. Here an equation is derived to find the damping ratio with the help of recorded data. So this is free vibration response of a system. Let Ui is the peak displacement after Ti time, and Ui plus 1 is the peak displacement in next cycle, next successive cycle. We can derive an equation that peak displacement after time E divided by peak displacement in next cycle is equal to e raised to power this expression. Taking natural log of both the sides, we get log of Ui by Ui plus 1 is equal to 2 pi zeta omega n by omega d. Log of Ui by log of Ui by Ui plus 1 is represented by a Greek symbol delta, and this is known as logarithmic decrement of damping. And this expression can be used to calculate the damping ratio. As you can see in the next slide, omega d is equal to omega n into 1 minus zeta square, and replacing omega d with this equation, we get delta is equal to 2 pi zeta omega n by omega n into 1 minus zeta square. So if we have recorded two successive peak displacement, we can find damping ratio of the system from this equation. For civil engineering system, delta is usually 0.05, but in any case it does not exceed 0.1. And if we take zeta as 0.1, zeta square will be 0.01, 1 minus zeta square will be 0.99, and under root of 0.99 is approximately 1. So for civil engineering system, the above equation reduces to this form. Now sometimes it is required to find the response of system after a specific number of cycles. And for that purpose, in this slide, we will develop an equation with the help of which we can find the response of a system after certain number of cycles represented by J. For that purpose, again the free vibration data is considered. Let U1 is the first peak displacement and Uj plus 1 is the peak displacement after J cycles. J is any round number, and we can derive this equation that the k in J cycle can be calculated from this equation, which after rearranging converts to this form. With the help of this equation, we can calculate the response after J cycles. क्या कोई सवाल है आप लोगों का? Okay, so let's proceed to an example. An empty water tank is shown and a free vibration test is conducted on the empty tank by applying a 60 kV force through a cable attached to the tank. The angle of the cable with the horizontal axis is 60 degrees, and stiffness of the system is such that the tank displays in horizontal direction by 2 inch. Having said that, the cable is suddenly cut, or it is suddenly released from the source. By doing so, the strain energy stored in this tank will start transforming into kinetic energy, and vice versa. And due to transformation of this energy, vibration will take place. And it was recorded that after 5 cycles, which completes in 2.55 seconds, the amplitude of displacement is reduced from 2 inch to 0.9 inch. Now, if the amplitude is reducing, this is due to the damping. With the help of this data, we are required to calculate the following parameters. So we will solve this problem by taking start with by calculating damping ratio, zeta. So it is given that after 5 cycles, the peak dynamic displacement is 0.9 inch. So J is equal to 5, Uj plus 1 is 0.9 inch, U1 first peak dynamic displacement, the peak dynamic displacement in first cycle is 2 inch, and we can apply this equation to find the value of zeta. J is 5, U1 is 2 inch, Uj plus 1 is 0.9, the only unknown is zeta. And if we calculate zeta, its value is 0.0254 or 2.54%. Next, it is required to complete the natural time period. For calculating the natural time period, you have to use the definition of natural time period. Natural time period is the time required by a system, single degree of freedom system, to complete one cycle of vibration during in the absence of force, that is during free vibration. Here it is given that 5 cycles are completed in 2.55 seconds. It means one cycle will complete in 2.55 divided by 5 seconds. So the natural time period will be 0.51 second. But remember, this time period involves damping. So this is damped natural time period. With the help of damped natural time period, we can find simple Tn natural time period. We have this equation: damped natural frequency is natural frequency into 1 minus zeta square. Taking reciprocal of both sides and multiplying with 2 pi, we arrive at this equation. Now 2 pi by omega is T. Therefore, Td will be equal to Tn into 1 minus zeta square divided by Tn by 1 minus zeta square under root. Or Tn is equal to Td into 1 minus zeta square. Value of zeta is just calculated. We can find Td is also calculated. We can find Tn, which is almost same because damping ratio is very small. Therefore, there is no significant change in the values of Tn and Td. Next step is to find the stiffness. So for that purpose, we need to apply the definition of stiffness. Stiffness is force required to produce unit deformation. Here we are considering stiffness in horizontal direction. In horizontal direction, the displacement is 2 inch under an inclined force of 60 kN. Now this 2 inch kip displacement is produced due to the horizontal component of this inclined force. And horizontal component of this inclined force is 60 cos 60. Stiffness will be therefore 60 cos 60 divided by 2. Or 15 kip per inch or 18,000 pound per foot. Next is to calculate the weight of empty tank. So there is a relation between Tn and mass. Tn is equal to 2 pi under root m over k. Omega n is under root k over m. M can be written as w divided by g, or kg by w under root. From this equation, we can calculate w, which is k into g divided by omega n square. Now omega n is 2 pi by Tn. Substituting the value of omega n, we have w is equal to kg into Tn square by 4 pi square. K is known, g is constant, Tn is also known. So just insert those values, you will get the weight of empty water tank, which is 74.9 K. Then viscous damping coefficient. Which can be calculated by using the definition of damping ratio, and which is 1455.3 pounds second per foot square per foot. And finally, number of cycles to reduce displacement amplitude from 2 to inch. That is, in how many cycles it is required to calculate the number of cycles such that the displacement, which was 2 inch at the start of free vibration, reduces to 0.5 inch. So we have developed an equation. From that equation, we can calculate the number of cycles, which is 8.69. Now, number of cycles shall be a round number, so rounding 8.69 will give us 9. So with this, module number 4 is complete, and you have already been assigned first home assignment, which you need to submit in 1 week time. And if your assignment is late even by 1 minute, it will not be accepted. You have enough time, so there is no excuse for not submitting assignment on time. अब अगर आप लोगों में से कोई जाग रहा हो तो सवाल पूछ सकते हैं. Okay, so we start module number 5. Module number 5 is related to the response of single degree of freedom system. In this chapter, we will discuss response of single degree of freedom system when subjected to harmonic forces, that is, the forces which change with time in the form of a sinusoidal curve. Further explanation, mathematically we can explain that a harmonic force is one whose time variation is defined by any one of the following equation. P of t is equal to P naught sine omega t और P naught sin cos omega t. इन दोनों में से कोई भी इक्वेशन से अगर आपकी हार्मोनिक फोर्स की टाइम वेरिएशन आ रही है, कोई भी इक्वेशन अगर से जो वेरिएशन आ रही है तो वो हार्मोनिक फोर्स को रिप्रेजेंट करेगी. In this P naught is the amplitude of harmonic force and omega n is the frequency of the force. This is not natural frequency, it is circular frequency of the force, which is also known as exciting frequency or forcing frequency. And with omega we can find the value of t, which is known as exciting period or forcing period, which can be defined as time required by a harmonic force to complete its one cycle, not one cycle of vibration, but one cycle of the force. Here, this first equation is plotted. Pt is equal to P naught sine omega t. And if you plot this, you will have a graph of this type. In this P naught, peak value of harmonic force, and t is time required by the force to complete its one cycle. The equations that used in this lecture are strictly applicable to sign variation of harmonic force. Pt is equal to P naught sine omega t. Example of harmonic forces are unbalanced in rotating machines. I gave you examples in first lecture that when unbalancing effect occurs in rotating machine, due to that reason the centrifugal forces are produced. Rotating machine can be any machine which rotates about its center, such as turbines, electric motors, generator, fans, rotating shafts. Now, just like previous lecture, we will first discuss the response of undamped system subjected to harmonic force, and then we will discuss the response of damped system subjected to harmonic forces. So first of all, let us solve the response of harmonic forces subjected to response of undamped system subjected to harmonic force. So as you know that generalized equation for single degree of generalized equation of motion for single degree of freedom system is of this type. If the system is undamped, this C is 0. If the forces are harmonic force, P of t can be represented by this equation, and the equation of motion for such system is of this type. अच्छा मैं एक फोन अटेंड करता हूँ, इसके बाद ज्वाइन करता हूँ आप